Okay, let's immediately start. Somehow here the table is so close to this whiteboard. This is strange. Then maybe we go up with this one. Then it makes it better. Good. Then yesterday our main topic was about adders. So let's quickly summarize what we did. So we had a lot of different adders, all with their individual, I would say, benefits and drawbacks. And we started with the ripple carry adder, which is, I think, was already known, but at a little bit different way to derive this, because, as you have probably seen, the same mass is always behind, and we just restructure the sum equations. So if we compare now this ripple carry adder as a baseline with some, let's say, serial adder, what are benefits, drawbacks when going from ripple carry to serial addition? Benefits and drawbacks of serial adder compared to RCA, ripple carry adder. Lower area, shorter critical path, so higher frequency. Any drawbacks? It requires more clock cycles, so it has a higher latency. If we now compare the ripple carry adder to a carry look ahead adder, what are benefits, drawbacks there? Propagation delay, benefit or drawback? Drawback, it depends. Yes, we have a long fan in and fan out. That causes for large CLAs a long propagation delay. On the other side, if we have a small carry look ahead adder, so only a few bits, then the critical path is shorter than the one for the ripple carry adder, so the propagation delay is shorter. So it depends a little bit on the size. Another drawback of carry look ahead when compared to CLA. So we have fan in, fan out. It's bigger, larger area. So carry look ahead requires more area because we do all this carry computation in parallel. Then what did we have next? We had the PPAs. So this parallel prefix adders. What is the, let's say, how do you construct such PPAs on a very high level? Not necessarily 4, but yes, you have a layer of half adders. What is this used for? Yes, to generate to construct this generates and propagates. What else do we need? So we have a layer with a series of half adders, which is a pre-processing layer. Then you said we have the XORs, which is a post-processing layer, right? And then, so we have here in between, we have some AND gates, OR gates, yes. We have formalized this in terms of this basic element, of this basic processing element. So what is missing here, effectively? What is in between pre-processing and post-processing? Yes. So what is represented here? The processing nodes are in there, the processing elements are in there, but the whole thing here, what does this represent? The processing elements is if I draw a node here. That's a processing element. And then we had structures like this here, somewhere in between. The logic depth is how many of these nodes we have. The critical path is the path with the most elements here in between. But the overall graph structure, what does it represent? Computation of what? Of the input of the carry? It is the computation of the carry. So that's actually a representation of the carry chains. Okay, so we have here in between a representation of the carry chains. What do we have to consider if we want to compute for a specific place, let's say some input here, Huh? Let's say that's index 5. Huh? And for index 5, we want to compute the carry. What do we have to ensure? So very generic, without a concrete implementation in mind. Which, how does this here relate to, let's say, the output of these half adders? Okay? So let's say we have here, so or something like this. Huh? I just remove this here for the moment, not to confuse you. And we only consider this carry bit that we want to compute. Huh? And you said, okay, we need from the layer above, we need the carries. Good. So probably I do the following. No. Is this sufficient? No. Why not? Yes. So for a specific index, we need to collect all the propagates generates here on the right. Yeah? So if I do the following now, I do it like this. So everything else is assumed to be computed in order, in the correct order. And no, there's something missing, maybe. And I want this one here to go there. Is this an adder? So if we collect from top to bottom, from bottom to top, our different combinations, what would this give? It would give us G. Okay, I should have started with 0, 1, 2, 3, 4. Yeah, would have been better. So I fixed this here to I equals 4. Yeah. Yeah. Just to avoid that I need to redraw something. Then I have G4. So this here is, let's say, this layer here, or after this one here, is layer we have dash. Here we have 2 dash. Here we have 3 dash. Yeah? So what we have here is G4 3 dash, P4 3 dash. Right? This is a combination of these two, which is G2 at G4 2 dash, P4 2 dash combined with, what is this? 4 3 2 1 0, G2 2 dash, P2. I can directly remove the dash because there's nothing in between. Huh? This is then G4 dash, P4 dash combined, and here we have G1 dash, P1 dash, and this is, not to forget, G2, P2, and this is G4, P4 combined G3, P3 combined G1, P1 combined G0, P0 combined G2, P2. Right? Is this an adder? Once again? Can this be an adder if we compute our carry like this? No. Why not? Yes. So the requirement is that we do the connection from the highest index to the lowest index. In this we can apply some mathematical rules, where we are associative. So it doesn't matter if we first compute these two or whatsoever. The second was we are idempotent. So we can multiple times compute the same thing. The third was it is not commutative. So it is forbidden to move G2, P2 to the right. So this here is not an adder. So we proved actually this is not an adder. What can I do to fix this? What can I do to fix this to make, at least for this carry here, this correct as an adder? Add another tree. That one. What do I have to do with this? Add a node to do what? swap the order. Right. So if I just remove this here, connect this here, this here, this here, then I would collect here G1. So this one here now is the same as here. Huh? Then we have G4 dash P4 dash, but instead of this, we would have this one here. So this here would become G1 dash P1 dash, right? So this here, P4 dash remains. Yeah? Instead of G1 dash P1 dash, we would have here G2 P2. Instead of this G2, we have here this one, which is G1 P1, G0 P0. So, and on the left here, this here would be then G4 P4, G3 P3 concatenated with this here or combined with this here. So we are correct. Yeah? So that would fix the issue, right? Again, the reason for that is we need to ensure that we have them in the correct computations in the correct order. We are not commutative. We are only associative and idempotent. Yeah? With this one here, well, you always have to keep in mind this one here corresponds to that, right? So if I draw it in this order here, I say the right input, so Gj is here Gj is the 2, G2. Yeah? So I have G2 here, and here I have this other part, which is G4, G3, G1, G0, yeah? Which is already some pre-computation. Yeah? And obviously, without computing what this actually is, obviously it matters if we first compute G4, G2, or G2, G4, right? So that makes a difference. So kind of just to visualize this, yeah, not necessarily 100% correct. We have a carry chain, yeah, which generates here an OR output, right? That is the carry chain as we have it in Ripple carry adder. Yeah? Now this goes into the next Ripple carry adder, huh? Where we have here somewhere this half adder stuff, and here's the carry input. Right? And this here goes to another OR, something like this. Huh? And then we have the next one. I just need one more, I think. Something like this. Yeah? Now putting this here down here is similar to just saying I connect this input to that one and this here to that, which is something completely different, right? That's the reason. Okay? So you need to ensure that you have the indexes in the right order. So G4, G3, G1, G0, G4, 3, 2, 1, 0, instead of 4, 3, 1, 0, 2. Only then you can you have computed the correct output. You need to be able to transform always back to this sequence from 0 to n or other way around. Okay, and then we looked into two examples here. The first was the Coggy-Stone adder, which has some specific properties. If we now compare this Coggy-Stone adder with the second one we have, with this Hank-Carlson, what does this Hank-Carlson do differently? So how does Hank-Carlson relate to this Coggy-Stone? The critical path is one longer. So if you transform want to transform the Coggy-Stone into the Hank-Carlson, what do you do concept-wise? Yes, that's a mathematical formulation, just to a more, let's say, more concrete explanation of this. So what I want to point to is Han-Carlsen effectively is for the odd passes, yeah, for the odd indexes, the same as Coggestone, right? We do exactly the same computation, we do it just only on the odd passes, right? So if you compare this graph here with the graph a few slides below, this one here, and you look only into this path, so only in the odd columns, huh? Then it's exactly the same, right? The difference comes for the even paths. Huh? So the even passes, like here, index 2, we do not do any computation until the odd passes are completely computed. And then we have one processing to generate the carry bit, right? So we have for the odd passes, we do exactly the same as before. Yeah? Until here, if you neglect or if you remove, just in your mind, you remove this here, this here, this here, this here, this here, despite of that note here. It looks exactly like the Coggestone, only that the even passes are missing, right? So let me see if this works out. Probably it does. So we have here this structure, right? And we have here this structure, right? And then we take one more. Do you see? It's exactly the same, right? So for the odd passes, it's exactly the same. Only for the even passes here, that we did here some computation that we don't do for the Han-Carlsen, right? So we do effectively the same as the Coggestone adder for the odd passes, and for the even passes, we take the result from the odd ones, and then we do one computation. We take just this input. Maybe I take one where I can somehow take the index. So let's say 0, 1, 2, 3, 4, 5, 6. So this is G6, P6. So we combine here G6, P6 with this path. And this path is on the very left. We have from here G0, P0 combined G1, P1. Then we have from here, we have this combined with here G2, G3. Then we have from here G4, G5, right? And then we do so this is what we have effectively from that path. And then we combine this with G6, P6, and then we are done, right? Makes sense? Good. Okay. Further questions to this PPA stuff? Good. Then we continued with this with two other adders, which were carry safe adder and compressors. Just from a purpose perspective, if we compare such a, PPA, RCA, whatsoever, with a carry safe adder, what is the difference regarding the use case? So PPA, RCA versus carry safe adder and compressor. Yes. So when would you use carry safe adder where you may not want to use parallel prefix adder? Always a good guess, but not the use case. Kind of, yes, but it's still not the use case. So maybe we draw the two basic things: the carry safe adder and the ripple carry adder. Yeah? How to draw a ripple carry adder for, let's say, 4-bit addition. So for 4-bit long input words. So we want to base this not on logic gates in the case, just on building blocks. So we have 2 inputs, another 2 inputs, another 2 inputs, another 2 inputs. Where did it go into? Yeah. So we have here full adder, here full adder, here full adder, here full adder. I just, well, this can also be a half adder. I just write the full adder here because it's simpler for me now. Yeah? So we have a full adder and put here the carry in to 0. Yeah? That's a half adder. Carry chain, that's ripple carry adder. Now I want to transform this into a carry safe adder. What do I need to do? If I only want a certain carry safe adder by rewiring, I don't need an additional layer. To have something useful at the end, I would need some, but only for the carry safe adder, I don't need. No, that's also not the adder itself. So yes, in practice, you need a register before, you need a register after, but you also need this for a ripple carry adder. Yes, same as here. I only want to transform the structure. Exactly. So we remove here this connect and have our carry safe header, right? So again, the question: what is the purpose? The difference in the use case? Exactly. Carry safe adder is for 3 inputs. Carry look ahead adder, ripple carry adder is for 2 inputs. Yeah? What comes out here is another interpretation. Yeah? So it's another mathematical interpretation effectively than a classical binary. Because classically you have here to the power of 0, here, so something times, of course, here something times 2 to the power of 1, here something times 2 to the power of 2, 2 to the power of 3, right? Now you have effectively 2 bits that are 2 to the power of 1, so these 2 bits that are 2 to the power of 2, 2 bits that are 2 to the power of 3, and still 1 bit here that is 2 to the power of 4. Right? So if we do this addition, what comes out is something that is another representation than a classical binary. So for instance, in this space, the meaning of, let's say, this here, however this is computed, yeah? I don't care about if this can ever come out, just to visualize. And this one here is mathematically identical, right? Right? That we also call redundant interpretation, redundant representation, because 1, 0 and 0, 1 have the same meaning. Yeah? No, at the end, to convert back into a binary, you need to sum up the lines. Yeah? So you need to sum up effectively, this is alone, these 2, these 2, these 2, and this one. Yeah? So we would have here then 0 times 2 to the power of 4. This here is 0 times 2 to the power of 3. This here is in both cases 1 times 2 to the power of 2, right? This here is 0 times 2 to the power of 0. This here is 0 times 2 to the power of 0, right? Yeah, you're right. Sorry. So
that would be
this one here is effectively, that line here is a 4. This line here is also a 4. It's just a different form to write a 4 in this space.
So after the calculation, 1 plus 1 times 4, right?
Yes. So this line here, if we set this sum bit of this full adder, the meaning is equivalent to we set the carry bit of this full adder. Okay. That is just what I wanted to point to, because this is some mathematical tricks sometimes used, and later we work with such redundant interpretation. Huh? Okay, so carry safe adder is to add up 3 bits, compress them into 2 bits, and then at the end we need to transform back, and this transform back can be done with any of the 2 input adders we had before. Yeah, so you can put a Cogestone adder here, you can put a ripple carry adder here, whatever you want, because you have 2 inputs that you want to add up. You just need to connect correctly. So these 2 are effectively then one input index for the next adder layer. Huh? Okay. And then we had this compressor where we did a small trick to convert effectively two subsequent carry-safe adders mathematically into XOR multiplexer structure, which is then more efficient to implement. Yeah, that's effectively all. The difference from a high-level perspective is we have now 4 inputs compressed to, we say, 2 outputs. Yeah? Plus we have an additional carry in and an additional carry out. Yeah? And then we can connect all of this, and we have one structure that can compress always 4 bits into 2 output bits. Again, here we have a similar effect. Maybe I draw this probably here. We have a similar effect as I had here. Yeah? So this one here corresponds to 2 power of 0. This here corresponds to 2 power of 1. This effectively is also 2 power of 1. Yeah? This here is 2 power of 1. This here is 2 power of 2. 2 power of 2. 2 power of 2. 2 power of 3. 2 power of 3. Yeah? So if we want at the end to make something useful out of this, we need to collect the right powers together, feed them into a 2-input adder, and finalize the result into a binary domain. Okay? Good? Okay. That was it more or less from our lecture yesterday. And then I wanted today first talk a little bit about different counter structures. Those I did not draw on the slides, but I will draw them here on the paper, and then I will later upload them with the written stuff. So, good. So, we had, interesting, okay, not sure why it doesn't work, so probably now. Okay, that's something completely different. What happens here? So we have already an adder, right? So with an adder, if we always add 1, we can also count, right? So why do we want something special? The main reason is, well, we can easily, with our adder, up and down count. We have maybe on FPGA specific resources for that. But since we have a full-blown adder and we do something very specific, we waste resources. Huh? Wasting resources in terms of we need more wires than we actually need. Huh? So just for instance, if you look into the Reupload carry adder, and you always want to add only 1, then for all besides the last one, you could actually fix 1 input to 0, which just removes this. There's an AND gate behind that somewhere. The AND gate is always 0. We can remove the AND gate. If we have this gate inside, an additional gate may cause, for instance, this. So I go quickly for the Reupload carry adder, just to show what I mean. This one here. So this one here. If we only want to add always 1, we could fix one of the A's to 0 for most of the inputs, right? Because we anyhow only add only for the LSB 1. This here becomes 0. The OR always forwards the signal from here, right? for most of the gates. Now, why is it better to have this? Obviously, if we opt out the AND and the OR gate, we reduce the area we have. The second thing is, each of these gates here switches depending on the value of B. Although B is only forwarded, the XOR here has some switching activity if B changes. The OR gate has some switching activity if this carrier changes. What does it mean for a gate if it switches? Well, not for the gate, but for a circuit if a gate switches. What is the, well, I said if we do not remove this XOR gate here, this AND gate, this OR gate here that we actually don't need for most of the parts, we switch them. What does this mean performance-wise for a circuit? Whatever gate. A generic gate. So here we have the case, if we want to count, that we could remove them. Still we have them in because we use a counter. And now my question is, why do we care? So one obvious thing is that if we remove them, we save area. But besides area, what else changes? It's faster because each gate adds to our delay. Each gate is a capacitor. What else? From where to where, and what does it mean? So if you consider the wires here in between, yes, but I would consider this negligible. Yes. So switching a gate means that for a short time we have a short current. Or a current from VDD to ground, we have dynamic power consumption. Right? So you always need both, right? Nobody with a half adder alone you cannot do addition because you have no carry in. Right? So effectively if you do the optimization then you end up in something like a half adder. But that's already specialization. So overall, if we go from a full-blown adder to a specialized counter structure, we have the benefit that we save power, we save time, we save area. Of course, we only save area if we do not reuse the adder anyhow for something else. So most of the time, any circuit has already, any digital circuit has already somewhere an adder. Just try now to make this here, probably it works. If I duplicate here. Okay. Then let's hope that it remains there. Wherever. Yeah, so most of the time we have already some adder somewhere, so that maybe the area is not the strongest benefit, area reduction, but we definitely save power, so energy, and we save delay. So we can increase, have a higher frequency. Okay, so with this said, it should hopefully a little bit motivate you why we do something else than just using an adder. And the first thing we can do is we just use something called a ripple counter. Ripple counter, how does this structure look like? Well, probably I'll leave this one here and put this one here. Or maybe the other way around, because this one is not so important. And more people sitting here, so maybe this one is better. Okay, now ripple counter is, we use effectively some flip-flops. Where is my zoom here? So we take a flip-flop, a chain of flip-flops, and we have some event that we want to count that defines our clock. So we want, for instance, to always count rising clock edges. We want to count every time we have some input data. So we have here Q and Q bar always, and then we connect Q bar here to the next input and feed it back, meaning if we have a rising edge here at the input and we initialize our circuit with all 0, yeah, so we have here some reset or init signal that resets our circuit to 0. Then with the first rising edge, the value of Q bar, which is 1, goes to 0. Yeah? So the internal state is 0, 0, 0, 1. With the next rising edge, the Q bar goes from 0 to 1. Huh? So we have first rising edge, first event. We have, let's say init. We have 0, 0, 0, 0. First event, rising edge. We have 1, 0, 0, and so on 0. Second event, we have this Q bar toggled to 0. So this is a 0. I toggle to 1. This here, this internal state here, which is effectively what I write here, becomes a 1 because we have a rising edge here for that. Next rising edge, we have here 1. Q bar becomes 0. If Q bar becomes 0, we have a falling edge. Nothing happens to the next flip-flop, so this stays. Fourth, we have a 1 here, a 0 here, because we toggle. Q bar goes from 0 to 1. So Q is 1, so Q bar is 0. If we toggle, we go here from 0 to 1. So this here becomes another 0. The Q bar, since this goes from 0 to 1, it toggles here the Q bar from the next, the input of the next flip-flop. And we have a 1 here, and so on and so forth. Huh? So we have just a binary, we get a classical binary sequence in this way, only by toggling the input of the flip-flop. Huh? We do not actually need any logic here. It just works directly. What is the critical path of this? So it's, to be honest, not completely obvious. Why? Because this is an asynchronous circuit. We have no clock here. We only run on the clock edge. So there are two different things we need to consider. The one is what determines the maximum speed we can count events. What is responsible for this? What is the, so the first question to ask is how quick can we count with this? So what determines the rate of events we can consider, the frequency of events we can count? Does it affect the frequency with which we can count events? So if you see here with some frequency that you can choose, let's say 1 gigahertz, events coming in. Yeah? What is the frequency of events we see here? Half. Quarter, eighth, and so on. So it's halves after every flip-flop. So if this here, this first circuit, including the setup hold time here, is fast enough, we have no problem, right? We can count with the maximum frequency that is seen effectively due to this feedback. That determines the frequency we can count with. This is the frequency we can count with, or determines the length of this feedback. So we can effectively be super fast with this. But assume we have all ones and here 0. What determines when we can read out the circuit? The correct result. Yes. So the path in sense, the critical path in sense of how long does it take until I have a valid result goes here through all of these things and then triggers our B3. That determines how long I have to wait before I can read out a valid state. Because in this structure, what can happen is that two different states are there at the same time. Yeah? So you can have effectively something like you are partially still in that state, partially already in that state. So the first flip-flop might be already be 0, the second is also 0, the third one is still 0, because the one did not yet really flip. So it is super fast in terms of I can really count high-speed events, but I cannot immediately compare to a reference, which makes it a little bit, I would say, for specific applications. Okay. Since we have a binary counter, we have flip-flops and so on, we also have a lot of toggles in here. So we may think of later if we can optimize for power. A second drawback here is that we actually need to wait, so we are not certain that after a specific clock we are done. We just can guess how long to wait, how many clock cycles to wait. For that, what we can do to avoid this asynchronous behavior is we can go for a synchronized counter. Synchronized counter, similar to that, is we take again some flip-flop, which is B0, B1, B3, B2, and so on. And then we put to all of these flip-flops here the event in parallel. Of course, all of this also needs an initialization. I just skipped the initialization. And the input to the first flip-flop should be some, there's a typo here, should be some feedback here, which goes again from Q bar. So now I made a mistake here, sorry. This one here is not connected. This one here is connected. Now, if we want to derive effectively the input here, the next bit for some specific point, we need some logic. So effectively, if you do this for 3 bits, the first toggle should cause 001, that we implement here with this feedback. The next toggle should cause 010. This here is already there. This here takes over the value from here, so that's also correct. And then we need to go for 011. There's something wrong. And then for 100, something like this one here. So 1 second, yes. Yeah, I just have to think because there's something in my notes here, in my reference is not correct. So I need to think how it should look like. So this one here toggles on the event. Here should be. Sorry, I provide this later or tomorrow maybe because I need to fix this because I need to sort this out and. There's some in the logic here I have in my reference is a mistake. Yeah, the point to make is effectively here we need to compute this forward path. We need to explicitly compute. So effectively that is kind of we take this this carry chain from our adder and we need to compute the next value from this addition just on the fly. That means that from here to here to here and so on, we have always longer and longer paths for the logic. I will show, as I said, I will show tomorrow morning quickly in the recap. I will show how it actually should look like. If I try to do this now on the fly, it will take me much longer than I want to take for that. and most likely I still have some error somewhere. So that is why I skipped this for the moment. Then we have want to optimize for gray counter for power. To optimize for power, what we can do is we can implement, for instance, a gray counter. Are you aware what a gray code actually is? So, any proposal what a gray code is? One bit changed at a time. How can we construct this? Yes, and then? So if you need to write down now a gray code, what would you do? So what you can do for gray code is there are different ways to construct this. Where do I have the correct notes? Don't remember, otherwise I need to do this on the fly. So there's no. Somewhere I lost my references, so I need to do it on the fly. Well, but that I can do. So effectively, we want to have a structure where we have always only one bit changed, and there is not a single gray code, but there are many different. One can be constructed by you start with 0, 1, then you extend this in the next step to you have 0, 1, prepend a 0, and you reflect on this line the last 2 bits here. So you have 1, 0, just this one here goes here, this one here goes here, and then 1, 1. If I now count, I have 0, 0, 0, 1, 1, 1, 1, 0. If I have an overflow, I go from 1, 0 to 0, 0. So I have for every step for this counter, I have 1 bit difference. If I want to extend to 3, what do? I put the same as before, just prepend a 0. I reflect this, put at the beginning a 1. So 1, 0 goes here, 1, 1 goes here, 0, 1 goes here, 0, 0 goes here. And if I look into this, here's 1 bit difference, here's 1 bit difference, here's 1 bit difference, here's 1 bit difference, here to here is 1 bit, here to here is 1 bit, here to here is 1 bit. So in that way, I could now extend this to an arbitrary number of bits just by doing always the simple process of prepend zeros, reflect, prepend ones. Another way to do that is you use a Carnot map, which is you use effectively such a base. So you use effectively, I should have the reference somewhere, then I could quicker draw this. Well, another way you can do this with a Carnot map, I don't do this here. No, doesn't really help. So, what is the benefit of such a gray code if you want to implement this? Since you have only 1 bit change, you have less elements that toggle, so you have lower power consumption. Yeah. It also helps you in case of transmissions. It can help you to reduce errors. Yes.
Even if the only difference.
Yes.
How does that?
Well, since we count only, we interpret still this here is a 0, this here is a 1, there's a 2, a 3, a 4, a 5, a 6, a 7. Just that now a 1, let's say a 3, now is written as 0, 1, 0 instead of classic binary. Yeah? So, if I count 1 upwards, so maybe I just do binary next to it. So binary is, right? That's a binary representation. Now if I go from, for instance, because that's the most interesting case here, if I go, for instance, from here to here, yeah, just counting up by 1, I need to flip here 3 bits. Here I only flip 1 bit. Yeah? And that makes lower power. Okay. Usually, if we do this, at the end we want to do a conversion into the binary domain. Yeah? So you may want to take your gray value and convert it into a binary. So, how does this look like? Well, what you can see if you compare here the gray side and the binary side, that the LSB obviously is the same. So, we have a bit, wait a second, once again. So, if we compare gray and binary, what we see is that the most significant bit is the same. Yeah? It's at least significant, it was not correct. Yeah? So we have here 0, here 1, here 0, here 1. Yeah? So if we start to convert from gray, bit, I have here only 2, but also bit 3. Yeah? Probably I should add here another. I just add here another times this gray code and a binary one just because I want to do this from 3 on. Yeah, that was just this one here. And then I need to do this reflection. And we have, was too much. We have, yeah, that is the gray interpretation. And the binary is, so maybe I make it quicker, 0, 1. Oh God. So I start making too many mistakes today. So, yeah, so that's the binary side. Now, if we want to transform this into from gray to binary, then we have here G, how to write this, G3, 2, 1, and index 0. Yeah? Yeah. So this is always a signal G. And we have here a binary signal, we call this B, and I call this 3, 2, 1, 0. Right? Now, obviously, the G3 and the B3 is the same. Yeah? So if we want to translate G3 into B3, we can just forward it directly. Now, if we want to go for the G2 to the B2, I need to collect, effectively, I want to translate this column here into that column here, right? What you can see is, in the upper part, just by the construction we did, this is exactly the same. In the lower part, it's exactly flipped. So, how can we implement this? Well, we have the first bit actually tells us in which part we are. So we can go from here to that just by an XOR. Yeah? So, we can take this G3 and another input G2, I should go here, XOR them together, and the output is B2. Yeah. Right? Then we can do the same trick for the next one, because here, if the second bit here is 0, then we have exactly the same. No, that's the wrong way. So, if the second bit here is a 0, here and here, here. On that side I need to check. If this is a 0, then this here is the same as on the right side. If this is a 1, then this here is the same as the inverse to the, not on the right side. If this here is a 0, then it's the same as here on the left side. If this here is a 1, then this here is just inverted. So, what I can do is, that was binary to gray. For the gray to binary, we have effectively in the upper half, if we have here a 0 and here a 0, then we have here the same. Yeah? So if these two bits are the same, then we have here 0011. If here and here is the same, so both 1, then here we have 0011. So if they are the same, is actually the outcome of this bit. So we feed in this here into another XOR, have here B1, and the second input is G1. And once more, for B0, that is, oops, actually I only wanted to have this one here G0. So in a case where these three are equal, we have here the output the same. In the case these three are not equal, in the case these three are not equal, so when they are equal, these two cases, and or when the, let's say when the XOR is 0, which is here, 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 here. In these cases, the value here at the output is the same as in the binary case. And in the other cases, it's inverted. And if here the XOR of the 3 bits is 0 or not, that is effectively the output for B1. Right? So we can take B1, feed it back into the XOR, and generate with G0 the B0. So that's what I have here. That's one direction. If you want to do this conversion for a large circuit, so for long counter, what is the critical path? Exactly. So we need to go through all the XORs down here. So if you want to compare effectively the outcome of a gray counter in a binary domain, we have to convert or have a long runtime to do this conversion. Well, if we only want to compare, maybe it's also fine to convert from the binary domain into the gray domain another counter. So, what is the effort for that? I just draw this down here. So, we have a binary input, and as long as I'm in the upper part here, I'm 0, in the lower part I'm 1. So again, we have now on the left side, we have B3. I've written like this. And B3 is just G3. Right? Now what is B2? So if we have B2, then in the upper part, we keep it. In the lower part, we invert it. Right? So if B3 is a 0, then we keep the value. If B3 is a 1, we invert the value. That's just an XOR, giving us G2. What about B3? B1. For B1, if here is a 0, then the output is the same. So if here is a 0, we can just convert this here to here. If here is a 0, we can just have here the same as here. If here is a 1 in the binary domain, then we have to invert. 1, we have to invert. So we just have another XOR here. And the same for the last bit. If bit 1 here is a 0, then we just have the output directly. And if B1 is a 1, then we have to invert. Right? Yes?
Isn't it an example? Isn't it like you're using the same kind of gates?
I use the same gates, but I use a different connection between them.
Yeah, different connection.
Yeah. And that has significant impact because area-wise it's the same. But here the critical path goes from Gn all the way down to B0. Here the critical path goes from any input to the direct output. It's 1 extra depth. This here is way faster than that was. Okay? So, at least for this encoding, you may choose another gray encoding, but at least for that encoding, you can much faster convert from binary to gray than from gray to binary.
I thought it would be the same amount.
Yeah. Good. So, if we have the choice, we go for what is better. What is so for this one? Good. Then I have on the slides, I only quickly want to go through this, not in very much detail. I have also a circuitry that implements a gray counter. Yeah? So you have effectively two ways to implement a gray counter. One is you do some memory stuff, and in the memory you effectively always point to the next memory address, and in the memory address that's your counter value and points to the next memory address. Yeah? Then you have a gray counter, which is relatively quick, but you require some read-only memory for that, or need to load the data for this memory page for it. Yeah? So has also some drawbacks. In particular, you need to have this load and store operations on your memory. Yeah? The alternative is you implement this as direct logic and without going into details. Yeah. So if you have time, you can go through this step by step, and you will see that indeed this forms a gray counter. The main point to see here is this gray counter effectively has here the event. Yeah? What I crossed here are just optional inputs for up-down counting for an enable of the counter, which you may have as additional control signals. And if you want to only count up, the remaining circuit looks like that. Yeah? And then you need to connect. This gives you 1 bit. So counting 1 bit is one AND gate with an inverter on one wire input, an XOR, another AND gate with an inverter in one input, and a flip-flop. Yeah? So it's relatively large. And, well, then you can connect these things to a longer structure. This is just to motivate that it indeed works. Yeah? The main point to see here is, let me see if I have this somewhere. The main point to see here is if you compute the output value of this after one event toggle, it goes here, the critical path from Q all the way till the last stage of such a gray counter. Yeah? So we have for every stage, we have at least one additional gate that forwards here the input. Yeah? And that means this structure, although it has only one toggle at a time, yeah, has a long critical path and also correspondingly a relatively low frequency. Yeah? That is the whole point behind that and what I wanted to say. Okay, this is a skip. Then I have two other counter structures which I quickly want to mention here. The first one is a ring counter that is very quick. So ring counter means nothing else than we have a sequence of flip-flops connected as a ring. We have the first one put to a set, the other one as a reset. These inputs here are connected as some init, and then we have the event going into the clock inputs. Maybe event that. So what does this do? It constructs a sequence which is initialized with a 1 and the rest zeros. If I have an event, this value is shifted 1 to the right, and the 0 is shifted in here. If I have another event, I have 0, 0, 1, 0, 0, and so on. Yeah? Until at some point I loop. Right? So in this counter, effectively the index of the flip-flop is the value I want to have, and the value the internal state is all zeros and 1, 1. Yeah? This is also called one-hot encoding. Yeah? what are benefits, drawbacks of this? So we can be super fast because we always shift only one bit without any logic in between. Yeah? It is pretty low power because we have no logic there, and we always flip only 2 flip-flops, nothing else. Yeah? The rest is stable, so no dynamic power consumption. Drawback, if we want to double the counter value for gray and ripple counter or adder, how many additional stages would we have in the previous counters? Well, it's binary encoded if we want to double one additional stage, right? How many stages would we have here if we want to double the numbers? So we counted till 3. How many flip-flops do I need to count till 6? Another 3. Yeah? So it's linear in the number of, in the counter value, the number of flip-flops. So it's relatively, it's not logarithmic, and therefore it's relatively area hungry. Another method to count is a Johnson counter. And so this was ring counter. This here is now Johnson counter. This is again similar to what we had for the ring counter. The only difference we have now is that here in the feedback we put an inverter, and our initialization is always a reset. Then we put the event here. So what is the sequence we will have? We initialize this thing with all zeros. Then if we toggle, the inverter causes that the input is a 1. If we have the next toggle of the event, we shift this 1 into the next register, this one here. The next bit here is overwritten by the one from here, so we have this sequence here. Yeah? Until all of this is a 1, and if this is the case, then the next event will start resetting the stuff until it flows over. Yeah? It overflows. So, benefits of this here compared to this one hot counter. So benefits from the ring counter that we had before to this Johnson counter. So what about area? If we want to count to the same number? Well, for the ring counter, at that point here, we would have an overflow, right? Because if we had 0, 0, 0, 0, 0, and so on, and a 1 at the very last, the next one would be 1 and the rest zeros, so we would back here. Yeah? So we spent for the Johnson counter 1 additional inverter, that's our additional cost, but we save at the same time 1 flip-flop if we want to count to the same number. Yeah? Right? So effectively the length here is overall halved. Right? Now if we look into this regarding, so that was area. If we look into this regarding frequency, it's roughly the same, right? Here we only have an inverter in addition. That's the only logic we have on top. Roughly it's the same frequency we can count. What about power? It's even lower power because at a time we only toggle 1 bit, right? So it's effectively a better choice than this one hot counting. Good. I think you have the next lecture, right? And so we are done for today, and talk tomorrow then about multipliers. So see you tomorrow.